Okay, welcome back to our tutorials on intro analysis. Um, so I want to look at an example on Leibnitz theorem. The fact about Leibnitz theorem is that if we have a product of functions that we need to differentiate to a higher number of times, for instance, like the example we are having here, like we want to differentiate the product of two functions. We have an algebraic function and a logarithmic function. We want to differentiate them 1000 times, or let's even say n number of times. What approach should we use to do that? So that is where Leibniz comes in. So Leibniz helps us to be able to differentiate this kind of functions a higher number of times, so to take higher derivatives of the product of two functions. So before we look at this, you must have gone through higher derivatives of some specific functions. For instance, the higher derivative uh, for the logarithmic function, and then a higher derivative for probably maybe the sine function. And so these ones you should know them. If you don't know them, for the logarithmic function, if we want to differentiate it n number of times for the ln x, we are saying that the generalization for this particular derivative is given as -1 power n minus 1 into brackets n minus 1 all factorial x power -n. So this is the general formula for differentiating the logarithmic function any number of times. So with this, you just have to keep this one in your mind. And for the sine function, this one is equals to sine of x plus n pi over 2, like this. This is the higher derivative for the sine function. But for now, we'll be looking at this based on the example we are having over here. So let's start. Let's see. Now the Leibniz theorem is given by, let's say, if we have two functions, u of x and u of v, and all these functions are differentiable any number of times, then we are saying that the differential of dn dx or n of u of x v of x, sorry, let me clean this one off. Okay, so we have this, the differential of these two functions. We are saying is equals to the summation of r goes to 0 up to n, then n factorial r, n combination r, then have d r u of x dx r times d of n minus r all over d of x n minus r v of x. So where u and v, so u of x is one of the functions and v of x is one of the functions. So this is the Leibniz theorem, and this is it. So we are going to apply this one in our the differentiation of our example. So let's see how we are going to do that. Now we have something like d 1000 x cubed ln of x squared dx 1000. So here our u of x is equals to x cubed, and our v of x is equals to ln x squared. But remember that this one is the same as 2 ln x. Okay, so for me, if I want to deal with this one, obviously we can write this as d x 1000, so x cube times 2 ln x, but this 2 is a constant. We can just write it as 2 outside d of 1000, the x 1000, then x cube ln x. So we can deal with this part. So when we finish, we multiply the whole thing by 2. Okay, so right now let's see. Let's start and see how we are going to go about it. So the thing is summation. So if we have so we have summation of r from 0 up to n combination r d r the r of x cube r of x cube, then the x r times d of n minus r, d of x n minus r ln of x, like this. Okay, but we know that n is equals to 1000, and so since n is equals to 1000, since this is summation, this part, since it's summation, so we will be taking the r at moment. So say that when r is equals to 0, when the r is equals to 0, the n here is constant for all the terms, so that one we will not touch it, but the r will keep on changing. Good. So when the r is 0, we'll have 1000 combination 0, the 0 x cube d of x 0 times d of n minus r. Our n is 1000, our r is 0, so that is 1000 minus 0, the x 1000 ln of x. But the 0 of x cube is the same thing. It means we are just differentiating 0 times, so nothing will happen over there. And here 1000 combination 0 is 1, so that is 1, so we have 1 times x cube times, now the differential of the ln x, we are saying that the formula is negative 1 power n. In this case, our n is 1000, because 1000 minus 0 is 1000, so 1000 then 1000 minus 1, sorry, then 1000 minus 1 factorial, then x power negative 1000. So this will imply that we will have x cube times negative 1 power 999, then 999 factorial x power negative 1000, like this. And this will imply that since this is odd, it will make the whole thing negative, and so we have negative x cube times x power negative 1000, then 999 factorial. And simplifying this, since the bases are the same, we add their powers, we get negative x power negative 997 times 999 factorial. So let me call this one equation 1. So that's equation 1. Now when r is equals to 1, so we have 1000 combination 1 d1 x cube d of x d of x power 1 times d. So here it will now be 1000 minus 1. Then we have the x 1000 minus 1 ln of x like this. So here we'll get 1000 combination 1 is 1000, and differentiating this one once, that will just 3x squared times here we'll have d 999 dx 999 ln of x. But remember, so this times this, you get 3000 x squared times negative 1 power 999 minus 1 999 minus 1 factorial, then x power 9 negative 999. So doing this, we get 3000 x squared times negative 1 power 998, then 998 factorial x power negative 999. So doing our arithmetic again, this is x power 2, this is x power negative 999. So adding the two powers, you get 997. And since this is even, the whole thing becomes positive. So we get 3000 x power negative 997 times 998 factorial. Let me call this equation 2. Okay, now let's go. We have when r is equals to when r is equals to 2. So we will have 1000 combination 2 d2x cube d of x cube square like this times d of 1000 minus 2, then d of x 1000 minus 2 ln of x. So differentiating this one 2 times, and 1000 combination 2 is 499. This imply that 499500, and differentiate this one is 6x times get negative 1 power 1000. So this will be 998, and so that will be 998 minus 1 998 minus 1 factorial, and so, and then x power negative 998 like this. So doing the arithmetic here, the whole thing will come down to negative 2997000 x power negative 997 times 997 all factorial. So let's call this equation 3. Now let's see, when r is equals to 3, so we have 1000 combination 3 the 3x cube times d of, so here to 1000 minus 3 d of x 1000 minus 3 ln of x. And so this 1000 combination, this and everything, when you do everything, differentiating this one 3 times give you 6. So you just have 166,167,000 times 6, and have negative 1 power So when you subtract this one will be 997, and here 997 minus 1 for the formula for differentiating lane x. That will be 997 minus 1 all factorial, then x power negative 997. And so when you do all this, you get your equation to be 9972000. Then we have x power negative 997 times 996 factorial, and let's call this equation 4. So now adding equation 1, 2, 3 and 4. So what is equation 1? So the equation 1 was negative x power neg 997 factorial plus 3998 factorial times the x power negative 997 plus minus. So here, let me use this color. So plus minus 29977000997 factorial x power negative 997, and then plus 9970020000996 factorial times the x power negative 997. So adding all this, we have this. Okay, but what can we do? We can factorize some things out. So you can factorize, let's see, we know that this x power negative 997 is common. It is here, and it is here. So we can factorize that one out. And what we do know is that 996 factorial is common to this, because if we want to express 999 factorial is equals to 999 times 998 times 997 times 996 factorial. So it means 996 is common to this. Okay, so we can actually do that and factorize that one out. Same thing, if we want to express 998 factorial, that would be 998 times 997 times 996 factorial. So this is also common, which we can factorize out. So with that idea, I'm going to factorize this one out also, including the x. Okay, so let's see. Okay, so we will now have okay, let me use, okay, so now we will now have x power negative 997, then 996 factorial out into brackets. So into brackets, what will be left here? We will now have 999 times 998 times 997 times negative 1. Okay, then we put this in bracket plus we have 3000, okay, times 998 times 997. Okay, already we've taken the 996 factorial out, so we have this one over here, then minus into brackets 2997000 times 997, okay, then plus 99700 2000. Already we've taken these two out, we've taken these ones out, so it will just left with this number which is here. So this will close the bracket here. Now doing all this, putting all this in your calculator, we will now have x power negative 996 factorial. Everything inside is 6, okay. So if you do everything inside there, it is 6. Okay, so right now we can then write as 6 over 9, sorry, can write as 6 over x power 997 times 996 factorial. But remember that we had something like there was a constant 2, okay, and then we had the 1000, the x power 1000 x cubed ln of x. It was x squared, ln x squared, but this is the 2 has come out, so this 2 is no more there, okay. So because of this reason, the differential of this 1 to 1000 times is this answer, but there is a 2 multiplied by it, therefore this implies that we now have 2 times 6 all over x power 997 times 996 factorial, and this is equals to 12 over x power 997 996 factorial, and this is your final answer for the question. So therefore we can then write, therefore d of 1000 x cubed ln x squared dx 1000 is equals to 12 x power 997 996 factorial. That's our final answer. Thank you for watching. Kindly subscribe.